Completion ordering is another consideration affecting latency. Here at the top, we have a FIFO ordered scenario. So in this case, each request results in 2 completion packets. And here in this scenario, we're supporting 3 outstanding reads. And those requests will come back in, first out order. So here, with the completion of packet 1, and in this scenario, each request is resulting in 2 completion packets. Then as soon as the final completion packet is done, then you can reuse that first request to initiate another request, which would typically happen out here. And here's request 2 and 3, the earliest that you can launch those requests. Now by comparison, if we look at the out of order scenario, the first completion packet happens more or less the way it did in the previous example, except now we're doing like a round robin scenario. So each of the open streams is going to get 1 packet, and then another round will complete those out. However, if this needs to be reordered, then we need to wait until this second packet shows up for the first request, and then only then can you make another outstanding request. So here you can see by comparison that the earliest that you can start another request is going to be different. That means that you've got just a fairly short amount of time for the root complex to do that completion unless you have a gap in data. Now, unfortunately, you don't have any control, typically in an endpoint device, about whether or not out-of-order completions are going to be used or in-order FIFO completions. Therefore, you need to design your hardware to be able to handle both scenarios. So this is a consideration for the hardware that you need to put in your endpoint device, as well as a latency implication. To summarize here, the lowest latency for single stream traffic, as we could see, is FIFO ordering. Also, fewer outstanding requests are needed in order to sustain full throughput. That's because you are able to recirculate those more quickly. Now, out of order has the best advantage for lowest latency when you have multi-stream traffic. In this scenario, if you have multiple streams with small FIFOs, then you can keep them more occupied. So in actual systems, as I mentioned, some use FIFO order, some use out of order. And so your root complex needs to support both. Typical PCI Express IP cores do not do the reordering for you, so this is something that you need to have additional logic for. Now let's talk about link efficiency. The specified link rate, PCI Gen 1, 2.5 gigatransfers per second, 5 gigatransfers per second for Gen 2, and 8 gigatransfers per second for PCI Express Gen 3, not all of this is usable. So for example, if we look at a by one link, which is at PCI Express Gen 1, this is 312.5 megabytes per second of raw bandwidth. So that's what happens when you just take 2.5 gigatransfers per second, one link, divide by 8. However, you've got to subtract out the 8B, 10B encoding, and this results in 250 megabytes per second. Now next you need to subtract out the link layer traffic overhead. So these are events like ACK, NAC, replay, and flow control updates, and so on. There's also packet overhead. So a packet, the actual data payload, is wrapped first of all in a header. So this is at the transaction layer. There's a header, so that contains things like address, first last byte enables, and that type of information. And then that gets wrapped at the data link layer to include things like sequence number and CRC and so on. And then at the PHY layer, there's the start and end bytes that are added to identify the beginning and end of a packet. So all this does not contribute to the actual data payload, but is an overhead. So when we plot that, then this is what it looks like for various payload sizes. So here, link efficiency, this is based on the efficiency after the 8B10B encoding has been subtracted out. So 100% would be 250 megabytes per second for a by one link. So here with payloads of let's say up to about 128 bytes, 256, 512, this is where we're starting to get into the 90% range, and so going to larger packets isn't really going to buy you too much. So now that we understand some of the theory behind what limits performance on a PCI Express link, now we wanted to do some experiments to determine what this looks like in real life and what could possibly limit throughput. So in order to do this, we looked at a by 4 endpoint device doing somewhere between 600 to 700 megabytes per second of DMA in each direction, connected to a host memory via root controller. This is a system that the baseline was a very small CPU utilization. In other words, it was running basically the DMA driver and some background tasks. And then we wanted to know what happens to the endpoint throughput when the host is placed under a number of stress scenarios. So these are scenarios like high CPU utilization, memory throughput, high I/O traffic, graphics applications, and so on. So the test results show that we saw only a very minimum degradation of throughput, DMA throughput. In other words, in a typical PC root complex, the memory contention is fairly minimal. So in this case, we were seeing only about a 6% worst case degradation on a number of scenarios that we stressed the system under. So we have developed sort of a rule of thumb for what is possible and reliable in a typical PC system. This is aggregating a number of data from a number of PC systems. And the number we feel that is safe to use is 150 megabytes per second per PCI Express lane per direction. And that would be doubled for Gen 2 PCI Express, and well, we haven't seen it yet, but we assume quadrupled for Gen 3. So in other words, that is a good design point, 150 megabytes per second, when you are developing your system that you can rely on.